Next, we have one more very important unit of refrigeration. And unit of refrigeration is what in actual practice? Did you heard the term ton?
TR, tonnage.
See, so don't get confused. One is a TON. TON is what? 1000 kg. We used to call 1000 kg is 1 ton. That is related to weight. But if I use the unit of refrigeration, I used to write TR. But we have a relation between these two, this ton and this ton. So how exactly we'll discuss. So first, this is weight and this is a cooling capacity or unit of refrigeration. So how exactly we got this, we'll try to understand. Let me read the definition first. You see, 1 ton of refrigeration is defined as the amount of heat energy required to melt 1 ton, nothing but 1000 kg in terms of pound is 2204, nearly 2000 pounds of ice. Or if you're getting confusion in pounds, just consider 1000 kg. Okay, so it's the amount of heat energy required to melt, say 1000 kg of ice at what? 0 degree centigrade, nothing but 32 degree Fahrenheit in water at constant temperature. In what time? Say 24 hours. We're considering this time for calculation point of view. So, okay, try to understand this. For example, consider this as say 1 ton of ice, nothing but 1000 kg, and ignore the sun. Assume that this is a room. This 1000 kg of ice I purchased from somewhere and I place in this room, and I'm going to close the door. So after 24 hours, again when I enter in the room, this ice, this solid will change to liquid, na? And why it will change from solid to liquid? Because extraction of heat, na? But extraction of heat from where?
Room.
Yes, from the room. So when you enter into the room, what do you think? The room temperature will be same as before 24 hours or it will drop?
It will drop.
It will drop, right? Because extraction of heat, because of melting of ice. And when you enter in the room, you'll feel the cooling effect. So that cooling effect we can call as 1 ton of refrigeration. Or technically, the cooling effect produced by melting of 1000 kg of ice. Say in 24 hours, we are considering time calculation point of view. So the cooling effect produced by melting of 1000 kg of ice is 1 ton of refrigeration. So this 1000 kg is ton. With that, we are getting the cooling effect. So we are calling 1 TR. So both are interrelated but different. Because of this ton, we are getting this ton. Because of this ton weight, we are getting this cooling effect. So we used to call the pronunciation is same, but the concept is different. Very simple. Got the idea online? So technically, we'll try to define this. Theoretical, I think you got the idea. It's simple. When you melt 1000 kg of ice, the cooling effect produced by melting of that ice, because you see melting of that ice required heat. With the extraction of heat, then only it will melt. Okay, so that extraction of heat is equal to 1 ton of refrigeration, nothing but 1 TR. And this is commonly used in the HVAC industry. I think you already heard this ton of refrigeration, very commonly used. One can use the kilowatt also for this capacity. But for cooling point of view, especially not for heating, for cooling point of view, we are using this ton, 1 ton or 2 ton, split AC, window AC, or 100 TR chiller, etc. Now we'll try to define this mathematically. See, simple. The latent heat of ice. But I think you have not discussed this latent heat. In the next pages only, you'll find this sensible and latent heat. At this level, remember, latent heat means the heat because of change of phase. In short, sensible is what? Okay, we'll discuss about sensible latent in the next page. At this level, just remember, latent heat means the heat because of change in phase. So in this case, the ice is melting to water, na? So change of phase. So because of change of phase, the heat is added or removed. That type of heat is called latent heat at this level. Okay, we'll discuss more about this in this chapter only. So you see, based on the experiment, we have this value. The latent heat of ice is what? 335 kilojoules per kg. Means for 1 kg of ice, if you want to melt, you need to provide how much of heat? 335 kilojoules. Kilojoules also unit of heat, na? In 24 hours. For example, we are considering for calculation. So therefore, 1 TR equal to what? 335 multiply with 1000 kg. In terms of this timing point of view, 335 multiply with 1000 divide with 24 into 60. Why 60? Because I want result in minutes. For example, commonly we are using this. So the result is what? 232.6 kilojoules per minute. In actual practice, considering the losses and other assumptions or other condition, we are considering this value as standard, 210 kilojoules per minute. 110 equal to 210 kilojoules per minute. So what you are getting with this? It means, for example, consider this is a room. In this room, if you want to produce 1 ton of cooling effect, what can be the rate of heat extraction?
210 kilojoule per minute.
Kilojoules means if you're using any equipment here in this room, and if you want 1 ton of cooling effect in the space, the rate of extraction should be 210 kilojoules per minute. So if you extract the heat with a rate of 210 kilojoules per minute, one can expect what? 1 ton of cooling. Similarly, if you want 2 ton of cooling, then yes,
one basic question is that if you set the temperature in different degrees Celsius for 20 degrees Celsius or maybe 22 degrees Celsius,
you
so
see that will do in the load calculation. What temperature, according to that, what in order to maintain the temperature, what will be the tonnage required, what will be the rate of heat extraction, etc. Okay, so I got your point, but at this level, I'm not talking about the load calculation. Just means the cooling effect. You see, what we learn is 1 ton of cooling effect is what? When you melt 1000 kg of ice. So the cooling effect produced by 1000 kg of ice is 1 ton. So same, if you want to produce the cooling effect which is produced by melting 1000 kg of ice, the same if you want to produce with the equipment, say cooling equipment, the cooling equipment rate of heat extraction should be
210 kilojoules.
Right, 210 kilojoules per minute. Okay, so what you're asking, I'm getting this, but don't go in that load calculation. For that, we have a detailed procedure. So at this level, the rate of heat extraction to get 1 ton of cooling effect. But how much cooling effect, or what will be the rate of heat extraction to maintain the temperature? That need a list of sources to verify, and we require detailed calculation. So we'll get what will be the rate of heat extraction to maintain the temperature to get that cooling effect. So at this level, simply 1 ton equal to what? 210 kilojoules per minute. In terms of BTU, we have 12,000 BTU per hour. It means if you want to produce 1 ton of cooling effect in a space, the rate of extraction should be 12,000 BTU per hour.
So one question is that we're saying that this machine is 1 tier capacity. This machine has the capacity to extract the heat of 210 kilojoule per minute. That is maximum capacity. We can alternately say that. Okay.
Yes, and you see, if the rate of heat gain is more than that, we cannot maintain the temperature. If the rate of heat gain is less than that, one can maintain the temperature. So that we'll discuss. We have a topic detail in load calculation. To maintain the temperature, that should be balanced, na? Q in should be equal to Q out. So at this level, just we are learning the concept of the capacity of the cooling. So see, in terms of BTU, this is also important for interview point of view. 1 ton equal to 12,000 BTU per hour. In terms of kilowatt, it's 3.5 kilowatt. And this kilowatt is not an electrical kilowatt. Remember, it's a mechanical kilowatt. Heat. Okay, so don't get confused. So remember, for example, if I consider 1 ton split AC, 1 ton split AC means it can extract 3.5 kilowatt heat, and this kilowatt is a mechanical. And for that, electrical kilowatt can be 1.2 to 1.4 kilowatt. That is electrical consumption. So electrical kilowatt is different, mechanical kilowatt is different. So this is mechanical kilowatt, not electrical kilowatt. Remember this. We'll use at the time of calculation. You may not get the idea at this level, but remember, this is not electrical kilowatt. This is a mechanical kilowatt, 3.5. And it's a fix. It will not change. Electrical kilowatt may vary based as per the efficiency of the equipment. Okay. So we have a range from 0.8 to 1.5 kilowatt per ton for electrical side. But that depends on the efficiency and other factor. But this is fixed. This is a conversion.
For 1 tonnage machine, how much electrical capacity required?
0.8 to 1.5 in between. That depends on the efficiency. But don't write. We'll discuss this at the time of machine selection. Or for interview point of view, you can consider 1.2 to 1.4. If you talk about split. In case of chiller, the case is different. The chiller start with 0.7. Again, in that chiller, we have a different high-class chiller or a standard chiller, etc. So that range will vary.
Yes, sir. For coordination point of view,
1.2 to 1.4.
Yeah, because electrical engineer is always asking about the electrical load of the HVAC.
You can consider in between 1.2 to 1.4 for a DX system. For chill water system, is going to be different. Next, so I think got the idea. What is the ton of refrigeration online? Next, we'll talk about enthalpy. So we start this chapter 3 with the heat only, no? So enthalpy is nothing but heat, just where we will learn in a technical way. Okay, so you see, enthalpy is what? It's the sum of internal energy, U, and the product of pressure and the volume. And in short, we used to call H enthalpy H equal to U plus PV. And as the pressure increases, what will happen to the temperature? Or if the temperature increases, what will happen to the pressure?
Pressure will increases.
Yes, both are directly proportional, right? And when you add the energy, that is a heat, so what will happen? Pressure increases. As the pressure increases, the temperature also increases. And remember, this relation we'll use at the time of vapor compression cycle, because at the time of compression, in a compressor, the temperature and pressure both will increase, but the volume decreases. That we'll discuss. So remember this, very basic, you see. Or in other words, you can say enthalpy is what? Heat transfer at constant pressure. Or practical or application point of view, heat content of the body is called enthalpy. This is a practical definition for interview point of view. Remember, enthalpy is what? Heat content of the body. Nothing but heat energy or heat. Okay. So that can be measured in kilojoules per hour or BTU, what we discussed at the beginning of this chapter 3. This example will help. You see, here inside, suppose a gas, and we are adding the heat. So what will happen? Adding the heat means we are increasing the internal energy. Adding the heat is a form of energy, no? So what will happen? You see, the piston will go up because the pressure and the temperature increases. So, and because of this, it will push up and the volume also increases. Okay, this concept will use at the time of vapor compression cycle. Remember, very, very important, because in vapor compression cycle, if you talk about the actual side, you'll find the different pipe sizes for liquid and for this suction, means for gas. So H equal to U plus PV is the equation for enthalpy. Just remember this, we'll use at the time of calculation.